Okay, so we are in Statistical Rethinking, second edition, chapter 11, and we're on question 11H2. So this has three parts, A, B, C, so we won't read them all at once, but we'll come to them one at a time, but we need to go in knowing this. Okay, so we'll be working with a data set that's called Eagles, which is contained within the mass package, so we'll have to load that. What this let's just look at the data rather than me trying to describe it real quick. So I've loaded it here. So I loaded the library for mass. I brought in the Eagles data, and I'm calling it D. And so here we have it right here. Okay. So what we have here is data on some eagles, and the idea is that there are pirate eagles and victim eagles. Okay, P for pirate, V for victim, and the victims have in their possession a salmon, and the pirate is going to attempt to steal the salmon from the victim. Okay, so that's what the data set is describing, and here Y is the number of successful attempts, and N is the number of total attempts. Okay, so in this first row, 17 of 24 thievery attempts or pirating attempts were successful. Okay. Now, P is described as either L or S. L describes large, so if it was a large pirate, they get an L. If it was a small pirate, it's an S. V also is encoded as large and small, so the victim was either large or small. And then A means, was the pirate an adult or immature? Not an adult. Okay, so that's what our data set is. All right. It turns out that, oops, I want to do this, that we will have to kind of process our data a little bit, and so we're going to binarize it. Okay, I tried to use index variables, but I couldn't get the quap to work. That will make sense here in a second. So I'm just binarizing the variables. So I have P2, A2, V2, which just reflect these variables. But if it's large, it gets a 1. If it's small, it gets a 0. Okay. Adults get 1. Immature gets 0. Okay. So I've just binarized my result or my data variables here. Okay. And now we are meant to. I'll let that run while I'm reading this. Now we're meant to fit a model using both quap and ulam. Okay. And it asks us to fit this model right here. Okay. So that's easy. So we're just going to plug this in as a model and then fit it with the two different methods. All right. So that's what I've done here. So I've just called an object model. So I can use the same one for both quap and for ulam here. So now this model is just what we have up here. So I won't go through detailing it. So we've just copied this model into our code. Okay. And we run it. And what we're asked is, does the quadratic approximation do okay? So keep in mind that the quadratic approximation is just an approximation. Ulam is actually sampling from the posterior. So all things being equal, we should trust ulam more. Okay. There might be times we want to use quap, for instance, when it does well enough, and the overhead for computing with ulam is just too much. It just takes too long or something like that. But we're running both of them and then kind of comparing the outputs here. So when we look at the outputs, so we can go through and compare these. Notice that the variables are out of order here, which is a little bit irritating. But when you go through and you look at all of these, quap is doing a pretty decent job here. And so I would say that it's probably doing okay given these particular circumstances. Notice that the prior distributions are very tight, and that is no doubt helping quap do a good job. If we were to have much looser priors, I suspect that quap would not do such a good job. But anyway, I would say that quap is doing a decent job here. Okay, so going forward, the questions are gonna say, well, in fact, the very next one is going to say, if quap is doing okay, use it for the rest of the questions. And I'm saying that it's doing okay. But I'm not going to use it. I'm going to use ulam because we have both quap and ulam models run, and we should always trust the ulam one better than the quap one. So I'm just going to ignore that piece of advice there. Okay. Okay, part B. So now we're meant to interpret the estimates So if the quadratic approximation is okay, then use it, but I'm just ignoring that. Okay, and plot the posterior predictions. Okay, So compute and display both the predicted probability of success and the 89% interval for each row, okay, of our data, as well as the predicted success count. Okay, so we're going to have actually two plots here, one counting probability of success and the other one using the actual number of successes. Okay, what different information does each provide? Okay, so first we need to get some posterior samples. Okay, so I've run that already. So I'm extracting samples from the model M ulam. So I'm extracting samples from the posterior distribution. And now with those samples, we can start to run just very easy queries about our data. Okay, so one thing that we might want is we can go through and start to look at the contribution of all of the different predictor variables. But the first one I'm going to do is just A, the intercept. Okay, so what is A representing all by itself? So if we go back up here to the model, A, or alpha, okay, this is representing the log odds when P, V, and A are all 0. In other words, it is the baseline probability when we have a small pirate, a small victim, and an immature pirate. Okay, so a small immature pirate and a small victim. Okay, that's what A is representing here. Okay, so so I can get the quantile, which is going to let me look at. So we want an 89% interval. So I just create that interval here. Okay, and then I'm also looking at the 50%, quantile, the middle of it. Okay, so so when we run that, okay, we get these values here. It's always just a little bit unfortunate how ugly it gets printed out here on Colab, but the 5.5% is about 39% success chance. The 94.5 quantile is about 76% chance of success, and the mean is about 59%, 58%, something like that. Okay, so in other words, again, when we have a small immature pirate trying to steal from a small victim, there is roughly a 60% chance of success in that situation. Okay, plus the credibility intervals here. Now, if we wanted to start looking at how the different values of some of the predictor variables were contributing, well, we could do the same thing, but now we are using the inverse logit, right? So I should have explained that. So so I'm taking the quantile of A from our posterior distribution, and I'm using the inverse logit. Why? What does the inverse logit function here do? The inverse logit takes log odds, which is what the posterior is in terms of, and converts it to probabilities. Okay, so that's what the inverse logit is doing. So I can say then that there's roughly a 6% chance of success. Okay. So here I'm doing the same thing, but now I've just kind of expanded my linear model. So now I have the probability of success when the pirate is large. Okay, because BP is 1 only when we have a large pirate. Okay, so I can run that, and again we get our intervals here, and already here you see that there's about a 95% chance of being successful, or something like that, like 90 to 98% chance of being successful. And we can just continue to run all the different combinations, or any combination that we're interested in terms of the predictor variables. Okay, and so now we need to plot these things. And again, we're supposed to plot this in two different ways. One is probability of success, and the other one is number of successes. Okay, so I guess you can just kind of look at the code here. So I don't know how much I'll go into this, but so here I'm creating a variable for the probability of success, which is just the number of successful trials versus total trials in our data set. Okay, and then I'm getting predictions using the link function, which again is part of the Rethinking package, right? It just creates the linear combinations and finds the mean prediction for each of the linear combinations of the variables in the data. And then I'm taking the mean of those predictions, as well as an 89% credibility interval with the pi function. Okay. Now, so that will be the data for the first plot, and so here's the first plot right here, and we'll look at that in just a second. Now for y sim, so now for plotting the counts, I no longer want percentages. I want the actual number that was successful. Okay, so I can actually now I can simulate from my model. Okay, instead of using link, I'm using sim to generate the number of successes. Okay. I am finding the mean of that as well as the credibility interval for that, just like we did above. Okay. If you wanted to, you could manually do the thing that sim and link are doing. When I work on my own projects, I tend to do that just because, well, I feel like I have more control and more understanding of what's happening. So now we're going to plot these next to each other. Okay, so I'm going to plot p success or my counts. Okay, and then to that plot, I'm going to add points that are representing either the predicted probability or the predicted count, y mean, and then add some error bars here. Okay, so let me open this in a new tab. Okay, so here's what we have. Okay, and the last part of this question is what different information is presented here. Okay, well, a couple things. So they're conveying similar information, right? You can see similar patterns across the two plots. Okay, let's get oriented. Sorry. So on the left-hand plot we have percent of success, and then on the right-hand plot we have the number of successes. Okay, and then we have the 8 different conditions. You could go through and label these conditions. Okay, I did not, but you could label these so you had a better, well, you could more easily see what they were referring to, although it would get very crowded down there. But what we have is the actual data is in these black dots, and then the mean is the empty dots, and then the predictive interval is the line through the clear dot here. Okay, so that's how we're reading these. So the information is similar, but notice, well, how do they differ? Well, one way that they differ is that the percent success plot has normalized the total number of trials, right? So in that sense, comparing, each condition to one another is probably easier to do on the percent success because it's conditioned on the number of trials, right? So for instance, like way over here, or which one? This one right here. So this last one, if you go through and you look at the data, there was only 4 times in which this condition applied. Okay, and so it would be, so this may, oh well, and over here there was close to 30, but normalizing these to the number of actual events kind of allows us to compare these more easily. Whereas over here, right, we have roughly a prediction of about 17, and here we have a prediction of about 3. But it would be very hard to compare these because there was only 4 trials here and there was close to 30 trials here. So is it really surprising that there's more successes over here? There was more trials over here, right? So the left-hand one gives us a better sense of maybe comparing the different conditions to one another. Okay. Okay, so now finally for C, we're asked to change the model a little bit by adding an interaction term here, okay? An interaction term between the pirate and victim size. Okay, so we have the same model except I've added this term right here, which needs a corresponding prior, which is given there. Okay, so I've already ran this, so we don't have to sit here and watch it run. You can look at the summary output if you want, but what we're asked to do is to compare the 2 models with WAIC, but I've done it with PSIS and WAIC. So I've already ran these. Okay. And so you see that the first model without the interaction term is doing marginally better, but I mean, not much. So for instance, both models get, a fair amount of weight, 70-30 here and 60-40 here. And notice that their PSIS scores or their WAIC scores are within, a standard error of one another, right? So really these two models are about tied. Okay. All right, well, I guess this one's long enough, and we'll call that good.